Okay, welcome everybody. So now we're looking at chapter five. Again, this is in your workbook. This is scale, drawings, and models. So this is where we're actually going to be drawing stuff that we see. Um, Now, as an example here, where's this useful? This is used in a lot of things. If you go into any type of design work, mechanics, engineering, even stuff is so, like even like IKEA. If you build IKEA furniture or Wayfair furniture, this is what this is. Again, just as an example here, here's an engine that's we call this an exploded view. We'll talk about that and stuff. So this is what it is. So it's taken a drawing and it is making an accurate uh, description of it. It's making an accurate drawing, which means things need to be sized very, very appropriately. For example, if I'm taking something and I say that, hey, this is a 5 centimeter line and this represents, I don't know, maybe 10 meters in real life, then I should be able to take a 1 centimeter line and that should be 2 meters in real life. So everything needs to be accurate here. Everything needs to be scaled. It needs a little bit of forethought before we jump into it. Now, I do strongly recommend that you guys use pencil for this. I personally, I love using pen. I was always my teachers hated me for it, but you need to use pencil for this. And if especially as you first start, you're unsure, you want to be writing light with it. You do not have additional extra isometric paper, which is what it's called. You'll see that later. So you do want to be writing really, really lightly at first. Because it's not really something you can do on loose leaf all the time, anyways. So in this chapter, you will use proportional reasoning to calculate the sizes of different objects. So what is a proportion? Well, this is when there's an equality between two rates and two ratios. I don't like that color. Now you're looking like this, like what does that mean? Don't worry, we'll get you taken care of. So for example here, example one, you can see there's a solution here, but the ratio of length to width of a rectangle is 5 to 3. So for every 5 units of length, there are 3 units of width. So for example, if I say that, hey, if I give you a 10 centimeter wide length rectangle, well, then it must be 6 width, right? Because this is just these times 2. It's that same concept. It's just going to be some harder numbers sometimes, but it is that exact same concept for everything. Take my number, times it by something, or divide it by the same number, and that's what the ratio is. It always has to stick that way. So, for example, here, if I were to, how can I draw a, no, I don't want that. Go away. Here we go. So if I were to draw a rectangle here, so you're noticing I can do it like this, blah, 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 blah. If I want it to be in the same ratio though, if I'm saying that, hey, here's a triangle, right? It's more wide than it is long. Well, now, it has to go in that same way. Or if I want to be a perfect square, and it has to stick, and you're seeing it's increasing at the same rate. Now, this is a 1-to-1, but it might be something as simple as this to this to this to this, and so on and so forth. So that's what it is. So if I give you a rectangle that is 24 centimeters wide, how long is it? Well, again, just like we know, so I know it's a 5 to 3. Again, there's a couple ways of doing this. I'll show you both. This is a throwback to the very first module. So it's length and width. Now I know that it is 24 centimeters wide, right? So just like before, oh, it's 3 times something gives me 24. How do I find that out? Go the opposite way. 24 divided by 3. Come on. There we go. Right? 24 divided by 3, it's 8. Our magic number in this case is 8. So 5 times 8 would give me the correct length, which is a 40. So it's 40 centimeters in length. Now, I could also do it as a fraction. Again, here, right? 5/3 is equal to, here's my length. I don't know what that is, but for the width, I know it's 24. And so you can do however you like, whichever works best for you. Some people really, the fractions just click better for them. And if that's the case, go for it. But you just got to structure it right. And you can see they have some solutions here that just shows that stuff if you need a refresher. Um, so at this point, I'll quickly go through unit one here, but you guys should be able to do one, two, three, four. You should be able to do A, B, C, D here really easily, right? Again, 8 times 168 is magic number. How do I find magic number? Go the other way. 168 divided by 8, 21. So 8 times 21 gives me 168, which means 3 times 21 gives me what this is, which is 63. So I'm going to trust you guys to be able to do B, C, and D with that and all these other ones. You can do it. I believe in you. I do quickly want to talk about what happens if it's like this, where it's at the end, or like we start with it. So in this case, again, I would need to go 4 times a number. 408 times something gives me 4, or 408 divided by something gives me 4, if that works best for you. But either way, I still go that opposite way. Take the two things you know. I know the top parts of these fractions. I'm going to stick with that. So 4 divided by 408 is, okay, so times 1 over 102. Like I said, if you understand what's happening here, you'd probably be smart enough to divide this instead, but I'm going to try and stick with this exact same thing I've been teaching the entire course. So, which means, um, so if I take, wait, sorry, did I goof this up? I did goof this up. My bad. Okay, I've goofed this up. Because we're not going left to right. We're going right to left in this case, right? So 4 times a number gives me 408, which means 408 divided by 4, it's 102 here, which means 9 times 102 would give me the correct answer here. I hope that makes sense. So if I go from left to right, if I go from left to right, you would be dividing 4 divided by 408. But because I'm going right to left, it's 408 divided by 4, right? We always work backwards. So 9 times 102 will give me 918. So you guys should be able to do all of these now. And just like before, you guys should be able to do all of these ones here. But I'll give you an example. So this one here, this is being times by a number, just a more complicated one, right? So I'm going left to right, which means I'm going to work backwards. So it's 12 divided by 5 to find that magic number. 2.4. So 5 times 2.4 gives me 12. 6 times 2.4 gives me 14.4. So x is 14.4 in this case. Again, you guys should be able to do all of these ones here. Right? Word problem, but it's done the exact same way, right? We have Tom to Mary, so T to M. Again, you could do a fraction, you could do however you want, but T to M, 3 to 4. We know Tom's 15. We don't know how old Mary is. You can obviously see here that, oh, it's 3 times 5, right? Which means it's 4 times 5, so Mary would be 20 years old in this case. So this isn't anything new. This is stuff that we've done at the very start of the unit, the very start of the class, sorry. We need these skills, though. They serve as the foundation for everything. Um, because now we're going into scale statements and scale factors. Now, a scale statement is a ratio that compares the size of the model to the size of the original. And I really want to make a key point of that. It is always model to original. Always, 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 always. Again, I really, really need to emphasize that. Now, if I were to give you a let's think of like the Eiffel Tower here. Sure. If I were to go and create a little, here's the little Eiffel Tower model, right? Now, maybe this is 1 meter in real life. Maybe this is 30 centimeters in real life. You know what? So maybe this model of that Eiffel Tower is 30 centimeters in real life. Well, the real Eiffel Tower, and I'm just pulling a random number out of my butt, I don't actually know, is 200 meters. Or, it's 30 centimeters, or sorry, actually 0.3 meters to 200 meters would be an example here of a scale statement. Or another way of thinking about this is we always want to get in the same units. 30 centimeters to, there's 100 centimeters in a meter, 20,000 centimeters. Well, if that's the case, that's like a 1 to, what's 20,000 divided by 30? And pulling around a number, about 1,667 centimeters. So this would be an example here of a scale statement. The model is 1 to 1,670th the size of the original. You also see these a lot in model cars. Here we go. Aging myself here. Rat rods. So these, for example, might be like a 1 to, these are usually like a 1 to like 56 or something like that, like a 1 to 32, which means the real one is 32 times bigger. But the wheel is 32 times bigger. The door is 32 times bigger. The light is 32 times bigger. But as you can see, it looks like the actual vehicle in this case, right? Because it keeps up with that scale. So that's what a scale statement is. So again, you have an example here that they give you, but model to the size of originals. Always model first. Now, a scale factor is the number by which the measurements of one object must be multiplied to give the measurements of the other object. What does that mean? This is the magic number, okay? Magic number. I've been using that word the entire time. This is the magic number. For example here, if a real car's head, that the model car's headlight here is like 50, like 1 to 53. This is an example here of a scale factor. It's 1 to 53, and it can be expressed as either a fraction or as a ratio in this case. Both of these mean the same thing, but it's always, model is always first for both of these things, okay? You always put the model first, whether it's on the left side or the top, depending on whether it's a ratio or a fraction. Very, 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 very important. It could also be going smaller as well. So for example, if I were to give you this model car example, you can see it's 53 times bigger. Okay? I know that's a lot. I promise you, we can simplify this quite a bit. So if I give you this one here, write a scale statement, and then calculate the scale factor. Well, the scale statement, you don't need to do this every time, but I'm doing it for this exact example. Normally, you can just give me the answer, and that's fine. For this one, though, and it's an example, I want to break down what I'm doing. So the scale statement is always model to the original. So I'm going to take the same side here, because these are the same original types of shapes, right? They're the same shapes, just bigger and smaller. Now, my model is 3 centimeters, or 3. My original is 6. It's a 3 to 6. But I can simplify that, right? I can simplify that. I can make that 3 times bigger. It's 1 to 2. And same thing. You could go like that, right? Where it's a fraction. Again, ratio or fraction, doesn't matter which one, whichever one works best for you. Obviously, your calculator can simplify fractions here a lot better than you can ratios, right? So 3 over 6 here, for example. Oh, that's 1 over 2. Now, so scale statement, boom, that's it. We're done. We're done the scale statement. Now, the scale factor shows how much bigger or smaller it is. I should take the scale factor. I can times it by the number and to get it. So I can take the model. I can times it by something to figure it out. So in this case, my scale factor is always equal to, again, the model divided by the original. Oops. Always equal to the model divided by the original. Now my model in this case is 3. My original in this case is 6. Turns into 1 over 2 in this case. Now in this case, they're the same number. That can happen. That's fine. But what happens if I go to this one here? Question B. Now, if you're looking, the model's actually larger in this case. That's going to change some stuff. So again, it's an example. You don't need to do this all the time, but the scale statement right? It's model to original. My model in this case, I'm going to pick the same side. I'm going to use the base, which is 15. I'm going to use the same base over here, which is 3, 15 to 3. If I simplify that, I can see it is 5 to 1. So that's my scale statement. Now my scale factor, again, model divided by original. Right? My model's 15. My scale, my model's 15 and my original is 3. I can see here that my scale is 5 to 1, which is the same thing as 5. If I tell you something's 5 times bigger, that means it's 5 over 1 times bigger. So I would accept both of these answers. I do recommend you try and keep it in fraction form, though. It just makes it easier. Again, always keep it in fraction form. If you were to tell me that it's actually, if you were to give me, hey, it's a 0.5, no, that's not okay. Keep it in, actually keep it in fraction form. Keep it in fraction form. Okay, done. Boom, boom, done. So again, what does the scale factor mean? I can take my original, I can times it by that to get to the model, right? I can take this 6, times it by 1/2 to get to 3. I can take this 3, times it by 5, which is 5 over 1, to get to 15. That's what that means. Okay? Um, oh wait, sorry. Did it ask me something? Oh, and a man in a photograph is 2 centimeters tall and his actual height is 1.8 centimeters. I almost skipped question 3. Now this one's really important. Centimeters, meters. Get them into the same thing. In this case, I'm probably going to go to 180 centimeters. But before I even talk about that, 1 meter is 100 centimeters, which means 100 centimeters is 1 meter, right? So I times by 100 or I divide by 100 respectively, depending on which way I'm going. 1 centimeter is 10 millimeters, or 10 millimeters is 1 centimeter. And also 1,000 meters is 1 kilometer, and 1 kilometer is 1,000 meters. So these are going to be the common measurements you see. So if you don't know those off the top of your head, you do want to write those down. Very important, because you need to have things in the same unit. So things need to be in the same unit. And now they are. Now they're both centimeters, right? So let's think about this. It's always model to original. My model is 2. So in the photograph, the man, if I take a ruler, I take a literal ruler and I measure how big he is, it's 2 centimeters. But I know that the guy's actually 1.8 meters or 180 centimeters tall. So it's a 2 to 180, 2 to 180 ratio here. I actually want to turn this into a simplified form. It's a 1 to 90 scale statement. Now my scale factor in this case, right? If I take my original and I times it by a number, I should get the model's size. So it's always model to original. I'm going to go fraction in this case, right? 2 over 180 simplifies to 1 over 90. So in this case, they're the same. So again, I should be able to take the original. I should be able to take 1.8 meters or 180 centimeters. I should be able to times it by that scale factor to get the real actual model size, which you can see is the case here, 2 centimeters. If you're still a little confused, I do recommend you read these solutions here, or please reach out to me. But this forms the basis for the entire unit. And we need to we need to have a good understanding of these ratios, because eventually you're going to be drawing stuff that follows that logic. We're not starting with the drawn just yet. Okay. Build our skills. So you guys should be able to do yeah, no, we'll start this one. I'll do question 5 with you, then I want you guys to try question 6 and 7. So the distance from Winnipeg to Vancouver to Winnipeg is approximately 1,880 kilometers in a straight line. And the distance on a map is 3.7 centimeters. Ding, 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 ding. We have different units. Gotta convert these bad boys to the same thing. Or do we? Not necessarily. You can keep it in centimeters to kilometers because it's not asking for the specific distance. So sometimes you can keep them in different units. That is totally fine to be able to go and do. That said, in my experience, people tend to get that. It's hard to apply in practice to know. So I do recommend try and keep them into the exact same units here in this case is usually a good idea. So I'm actually going to convert these kilometers into centimeters. So I'm going to go from kilometers to meters to centimeters, right? So to go from a kilometer to a meter, 1 kilometer is 1,000 meters. So I got to times it by 1,000. So it's going to be 1,850. 1,8, and I add through 3 zeros, right? 1,000 has 3 zeros. 1,850. Now I got to turn that into centimeters. So that's that many meters. 1 meter is 100 centimeters. So I just got to add 2 more zeros, right? So 18500. 185 million centimeters. That's what that is. Okay, so scale factor, right? Model to the original. My model in this case is 3.7 centimeters. My original in this case is 185 million. But this is the scale factor. Now, I do want to simplify this as further as I can. I do want to scale, sorry. No, I did this right. Okay, model to original. Okay, so just like before, so 3.7, your calculator can do that for you. Dude, 9 over 252.5 million is the actual scale factor here. So a little bit confusing, right? A little bit convoluted, a little annoying. I get that, but that kind of just is what it is. I'm just checking something. Sorry. Now, so again, I really want us to think about this here. I can take my original, I can times it by the scale factor. To get the model size, right? I can kind of do it. I can kind of mix it up a little bit too, though. I can mix it up a little bit too. Another way of thinking about this is I can take my 185 million, I can divide it by my 3.7, and I'll actually get 50 million as a scale factor. So it depends on how you use it. These are technically the same thing. And I know that seems confusing, right? Again, I can take 3.7 centimeters. I can times it by 50 million to get this size, to get 185 million centimeters. That works. I can take 185 million centimeters, times it by this to get to 3.7. So either of these answers would be acceptable. You can see obviously one of them makes a little bit more logical sense too. So I know it's a little confusion, but that you'll get it. It'll make sense as we keep going. So I want you guys to try out questions 6 and 7 here. I'll actually go through these answers a little bit. So pause the video, try them out as best you can. 3, 2, 1, pause. Okay, so for question 6 here, 6A, write a scale statement, right? So if I give you an original human hair, pull a hair out, and I say, I'm going to zoom in on it 200 times. I have an original and I have a model. And the picture of the zoomed in hair is the model. Now, in this case, so they're just saying, hey, it's magnified by a factor of 200. I don't know how wide that actual human hair is, but I know that I've taken an original, I've made it 200 times bigger. So in this case, it's a 200 to 1 or a 200. These are both acceptable. is a scale statement. Now for this one here, so what if I give you I take a photograph of a hair, and in that, if I take a ruler, again, I take a ruler, it's 2 centimeters wide on my model. What's the actual width, model and original of it? So, right, so again, you can do this fraction, you can do this as a ratio. I like fractions just because it's a little bit easier. So model to original, right? I know it's a 200 to 1. We've talked about that up here. And I know that my model is shown as 2 centimeters. Well, 200 times something gives me 2. 200 times something gives me 2. Reverse magic number, 2 divided by 200 gives me 1 over 100, which means 1 times 1 over 100 will give me the actual answer. So 1 times 1 over 100 gives me 0.01 centimeters in this case. Now for this one here, question 7, same thing, 3, 2, 1. So you should get something like this here, right? Model to original, 5.4 to 193. Now, technically, you could use your calculator and you get this thing here. I want us to go a little bit deeper here, though. I want us to actually figure out, I don't want some weird decimal in there. I want to know, hey, for every 1 centimeter on the hockey card, it's this many centimeters in real life. So what I'm actually going to do is I'm literally going to take 193, going to divide it by 5.4 in this case, to get 35.7. So it's a 1 to 35.7 ratio here. So you do want to try to have one of the figures be a 1. Again, 1 centimeter should equal other centimeters. It's that important. So it's really important to try to be able to do that. Yeah. So example 3 here. Oh, on a blueprint, a quarter of an inch is equal to 1 foot. One thing to note is that 12 inches is 1 foot in real life. So a quarter of an inch is equal to 1 foot. Now we want to write this in. We want to write this as a scale statement form, and again with the form 1 to x. Sometimes this matters. Now up here, what did I do? I literally took the bigger number, divided by the smaller number. It's really kind of how it works. Or I took one of the numbers, I divided it by the other one. It's really how it boils down to. So for this one here, again, we got to get this into the same units. We got to get this into the same units here. So in this case, quarter of an inch is 1 foot. So we're saying that. Actually, I can stick in. I can keep it like this. So 1 over 4 is equal to 12 inches. We're going to put this one as 12 inches. You could go the other way around. Doesn't matter. You get the same answer at the end of the day. So 1 over 4 inches on a blueprint is equal to 12 inches in real life. If I times both these by 4, I'm going to get 1 to 48 ratio here. Or I could have said that this is 0 point blah 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 of a foot. A little bit more annoying to be able to do that. So it'd be a 1 to 48 in this case. And as I can see, it's written in the correct form, so we're good to go. Now, what's the actual length of a room that measures 3 3/4 of an inch on the blueprint? Again, model to original, model to original. This is my model. I'm trying to find the original. So here's what I know. I know it's a 1 to 48 ratio, and you can do this as a fraction as 1 over 48. I know that I have a 3 3/4 or 3.75 is equal to some type of an original that I'm trying to find. Right? So think about it. 1 times a number gives me 3.75. You can literally just eyeball this one. So 1 times 3.75 gives me 3.75. 48 times 3.75, 180. So it is 180 inches in real life in this case. Now you could turn this into feet as well, I guess, if you wanted. It doesn't specify, so it's the same thing. Okay. Do-do-do-do-do. Let's try this one here out, 8, and then I think you guys can do the rest of these. So we'll try out 8 here. So in a picture, a man measures 2.3 centimeters. So this is our model. His actual height, which is the original, is 1.78 meters, which is 178 centimeters. Now he is standing beside a flagpole that measures 7.6 centimeters in the picture. What's the actual height of the flagpole to a meter? I can find my final answer here in centimeters, and I'll just have to convert that into a meter later, or I can put everything into meters, and that'll spit up the answer. I recommend let's go to centimeters, just because I don't want to. You don't want to work with 0.023 meters. That's annoying as hell. So we're not going to do that. All right. So just like before, model to original, right? Always model to original. I know it's a 2.3 to a 178 ratio here, which if I simplify that, 178 divided by 2.3, it's a 1 to 77 point, was that 4? 0.4 ratio here. So I have that. Perfect. So that's our actual scale here that we're using. Now, which means I can now apply this to this flagpole. So I know I have a 1 to 77.4 in the flagpole. In the model, it's 7.6 centimeters. So I can use that now to find the actual height. So, right, so 1 times 7.6, that's why we turned it to 1, gives me the answer, which means 77.4 times 7.6 will give me the answer as well. So 588.24. 588.24 centimeters. You could also just put 588 centimeters in this case, and that would be fine. Now, I'm not done though, because I need to turn this into meters. If I turn this into meters, boom, boom, move it 2 decimal places, it's 5.88 meters. Correct, but that's not what it's asking. That's for the nearest tenth. It only cares about this, so I got to round it to 1 decimal place. It's 5.9 meters in real life is how tall that flagpole is. Now, at this point, we have to do we just have to do a sanity check. Does that seem right? Is a flagpole going to be about 5.9 meters, about 6 meters tall? Yeah, that's it. That sounds right. Sure. Yeah. Just do a logic test, right? If I were to tell you that this flagpole was it's 0.5 meters tall. No, it's not. It's not in this case. So yeah, we're correct here. So at this point, you guys should be able to do all of these and then work on your practice questions here as best as you can. If you have any questions, please let me know.